Welcome everybody to the top of page 111 in the workbook, and this is the continuation of example 2 that we started in the last video, where we had defined a function a of x in terms of this function g of x. And the first thing I want to point out here is that we plotted some points on the previous page, and so what you see over here in the graph to the right, the points that I've plotted are exactly the same points, that we plotted on the previous page. And they came from the table on the previous page. And so I'm just going to recopy the values of a of x from the table on the previous page. You can look back and see that these are exactly the same numbers. And the goal of this second part of the example is we'd like to see if we can draw an accurate graph of the entire function a of x. We've got some points, but we'd like to complete the entire graph. And the key to doing that is remembering the relationship between these two functions a and g. Remember, on the previous page, we convinced ourselves that g is the derivative of capital A. Keep that in mind as we go through this problem. That's going to be the key. All right, so that said, let's start with part C of this. They ask us on what intervals is the function a of x increasing and decreasing. Let's start with the increasing part of that. Well, what we have to help us answer that question is the derivative of a. So how do we tell how a function increases based on its derivative? The key, again, is remembering that a function increases where its derivative is positive. In other words, we're looking for where the derivative graph is above the x-axis. So going back to the graph of a prime over here, notice that it's above the x-axis on this stretch between 0 and 1.5, and then again on this stretch from 4 to 7. So those should be our two intervals of increase for a. What about decreasing? Well, same idea, only now we're looking for where the derivative is below the x-axis. And we can look up at our graph and notice that the only place that a prime of x is below would be from here to here. That looks to be between 1.5 and 4. So that's our one and only interval of decrease. So we have finished part C. We're ready to move on to part D, which asks us about local maxes and local mins. All right, so let's first think about local maxes of A. Well, where would that happen? Well, let's maybe remind ourselves kind of what a local max looks like. So if we drew a little snippet of the graph A where it has a local max, it would kind of look like that. And what you might notice is that kind of what's happening with the derivative on both sides of that. So on the left side of a local max, you see how the function is going up, so its derivative would be positive, and on the right-hand side it's going down, so its derivative would be negative, which means that we can identify a local maximum point by looking for a place where the derivative changes signs. In particular, where a prime changes from positive to negative, above to below. Do you see any points back on the graph of the derivative up here at the top where the derivative graph goes from above the x-axis to below? I see one point right here at 1.5. Our graph is above the x-axis to the left and below to the right, so 1.5 should be a local maximum then of A. And local minimum, other way around. There we would be looking for a place where a prime changes from negative to positive. So are there any places up here again on the graph of a prime of x where we go from being below the x-axis to above it, I see one point right here at 4. We go from below to above, and so that should be a local minimum of A. Okay, so I believe we have taken care of part D. We're ready to move on to E. And just to warn you, I'll probably be doing a little bit of scrolling up and down here because our graph is out of the picture now. Okay, so what about the question of concave up for A? Okay, that's kind of an interesting question because normally we need the graph of the second derivative to answer questions about concavity. A function is concave up where its second derivative is positive, but we don't have a graph of the second derivative, we just have a graph of the first derivative. Okay, so what we can do here is to remember a relationship that we've mentioned before. The second derivative of a function is going to be positive when the derivative is increasing. Okay, because if the derivative is increasing, its derivative has to be positive. That's kind of the logic of that statement. All right, can we take that observation maybe and figure out where A of x is concave up now? Okay, well again, we are looking for intervals where A prime is increasing, where it's going up. Okay, so with that in mind, let's scroll up and take a look at the graph of the derivative again. Okay, so that's this graph up here that we keep going back to. Where is that function increasing, going up? I see a couple of intervals where that's happening. Okay, let's get rid of some of these points that we've already labeled. Okay, so one interval of increase would be from here to here, it looks like, 0 to 1, and then I see one more here where the graph is going up, and that appears to be from 2 to 6. So that means that 0 to 1 and 2 to 6 should be the intervals that we're looking for. All right, so let's scroll back down and fill those in. Okay, to figure out where A of x is concave down, it's exactly the other way around. We're looking for where the derivative graph is decreasing. Okay, do you see any intervals like that, looking back at our function? Okay, well I just see 1 from here to here, and that appears to be from 1 to 2. So 1 to 2 should be an interval where the original function is concave down. Okay. So we've completed C, D, and E, and it puts us in a position where we've got enough information where we can maybe draw a more accurate graph of this function A. Okay, there is one thing that I'd like to do before we do that, one piece of information that might help us do that. And it kind of goes back to an observation that we made up here in D. The fact that we have a local maximum at x equals 1.5, 1.5 is not a particularly nice number. It's not on this table of values that we have up here. So I'd like to see if we can figure out what the value of A is at 1.5, just so we can add a point to our graph. All right, so let's scroll down here and see if we can figure that out. So A of 1.5, by definition, if you look back at the definition, it's the integral from -1 to 1.5 of our function Okay, and I'd like to break that up into two pieces. Okay, if we integrate from -1 to 1.5, we could first integrate from -1 to 1, and then from 1 to 1.5. Okay, whoops, I'm writing f of t, but I mean g of t. Let's fix that. Okay, and the reason that I do that is we already know what the value of the integral from -1 to 1 is. That's just the value of our function at 1, which we can get from our table. Okay, if we scroll up for just a minute, A of 1 is this number, 1. So we already know what that is. What we need to figure out is the second part of this, the integral from 1 to 1.5 of g of t. That comes down to area. Okay, so let's scroll up to the function g and see if we can figure out what that integral from 1 to 1.5 is. Okay, well here's 1 and here's 1.5. Let's first get rid of some of the shading that we have here. Okay, so 1 and 1.5, that's this really tall, skinny triangle that we're looking at here. And the question is, how much area is that? Well, if you look carefully, the base of that triangle is a half, and the height is 2. So if we use 1/2 base times height, we can figure out what the area of that is. 1/2 base times height. You can do that arithmetic and notice that we're just going to get 1 plus a half, which is 1.5 out of that. Okay, so what we figured out here, and just to warn you, I'm going to scroll up in a minute here again. We substituted in 1.5 and we got out 1.5, so we've got a point on the graph of A that looks like 1.5, 1.5. Okay, let's go up here and plot that. So 1.5 is here, and y equals 1.5 is there, so we've got a point that we just added. Okay, now let's see if we can draw this graph kind of piece by piece. All right, so we're starting over here at x equals -1. You can look at the graph of g and see that it's right on the x-axis, so we're not going to get any area out of there, which means that our start to the graph of A is just going to be flat. Okay, and then we come to the stretch between 0 and 1, between here and here, and you can look down at the work that we did and notice that we showed that the graph has to be concave up between 0 and 1. So when I draw this stretch of the graph, it should have kind of a ball upward shape to it. Okay, and then we've got a local maximum at that point, and between 1 and 2, you can look at our work and notice that the graph was concave down, so this should have a ball down shape to it on the next stretch. Okay, and then we come to, and for this I'm going to scroll down again. You see how we're concave up on the entire interval from 2 to 6. Okay, if we use that fact, and the fact that we have a local minimum at this point, that means that we should have a big ball upward shape all the way from 2 to 6. So our function, if we go through the points that we've already plotted, would have to kind of look like that. Notice that it's concave up on that entire interval. And then finally, we've got this last little stretch of our graph from 6 to 7. What's going on there? What's the concavity between 6 and 7? Well, notice that if you look at our answers to E, we're neither concave up nor concave down between 6 and 7. What is that saying about the shape of our graph? Well, if we're neither concave up or concave down, we have to be linear, which means that this last stretch should be a straight line. Okay, and so there's our more accurate graph of A. And you can maybe take a minute, we're at the end of the video here, and just confirm that you agree that we drew that graph correctly based on all the information that we gathered.